All right, everybody, and thanks for tuning in to this daily space weather supplemental. What we're looking at is a series of coronal mass ejections from the closest star, otherwise known as El Sol. And stereo A, for you new viewers out there, is located at a place called Lagrangian point 5. So there's an equilibrium point when it comes to gravity. It's very easy to put an object here at L1 or here at L5, where stereo A is located, as it will remain gravitationally bound to the Earth, and it will just essentially follow Earth on its orbits around the Sun. So we've got this spacecraft there. It gives us a great view of Earth-facing coronal mass ejections, one of the more important instruments we use for this. We also do see some ejecta headed toward stereo A. You can see this halo-like appearance around the obscuration disk from its coronagraph instrument. It's that black disk that hides the extremely bright sun to provide the contrast to see plasma being ejected out of the sun's atmosphere, known as the corona. Now we've got some data here from Lagrangian point 1 also. Now what we're looking at is the Lasko C3, so part of the SOHO spacecraft at Lagrangian point 1, about 1 million miles toward the Sun, at the equilibrium point directly in between the Earth and the Sun, shown here on this little visualization as L1. And frankly, what I would say is that some of this ejecta will be likely to strike the Earth. So I want to make a pretty short video about this here. I don't want to harp on this for too long, but I would expect some of this ejecta to strike Earth. Here's some more imagery of the Sun. So here's a spectacular composite view here featuring both this morning's coronal mass ejections and this afternoon's coronal mass ejections. And with that much material coming out of the corona, folks, you could place wagers on whether or not that is going to strike the Earth. Some aspect of these coronal mass ejections will most assuredly strike the Earth with near 100% certainty. So while the main mass, you can clearly see, is likely to miss the Earth to the northwest and west at the beginning, and to the southeast and east at the end, perhaps these are connected filaments. It is very hard to say for sure what the shape of these things truly is, but the initial analysis certainly shows some ejecta striking the Earth's magnetosphere. So here's another view here. This is zoomed in, and the time frame here is about 1900 hours yesterday on the, what is the date? On the 21st. So yesterday on the 21st at about 1900 hours through today, May 22nd, at about 2200 hours. There were a series of C-class flares and now a couple of M-class flares also out of this fairly simple sunspot group here. So, and regarding whether there is not possibility for additional coronal mass ejections, there indeed is, as I can see some plasma filaments are still indeed there on the Sun's surface. So some of this plasma splashed back down on the Sun, some of it is still suspended out in the corona, and some is headed our way as well as off to the northwest and to the southeast. So here is a full disk image, and this is 1600 angstroms here. This is ionized carbon. And you can see carbon likely being made there, those bright areas, those sudden increases in the amount of carbon visible, the brighter zones, folks, those correlate with larger amounts of carbon in those areas. So you can see the area associated with the sunspot's umbra there, the really dark spot, has almost no carbon, but those very bright regions suddenly have lots of carbon. So, some interesting spectroscopy there in 1600 angstroms. Here's another wavelength. This is ionized iron in 193 angstroms. And you can see the reverberations of those solar flares looking like ripples progressing across the sun. Clearly wave-like patterns, an indication that the sun has a real surface. Fantastic imagery there in 193 angstroms from the Solar Dynamics Observatory. We've got some close-ups first, some more wavelengths here. So here's the spectacular full disk imagery at 304 angstroms. Now you're looking at ionized helium. And again, I would note that there are still lots of filaments that have not ejected yet. So there is still a capacity for additional coronal mass ejections even after seeing all of this. And before we go on with more imagery of the sun, let's look at some other data here. First, we'll take a quick look at the X-ray flux. And there's a 3-day chart of the GOES X-ray flux, and you can see 3 C-class flares there and 2 M-class flares. And the last one kicked off as we did the show. So once again, flares happening at opportune moments. We did see radio blackouts here, which are basically openings in the ionosphere where instead of your radio signal being re-emitted, they get absorbed. Deabsorption predictions. So we experienced some radio blackouts here. You may have seen a couple little errors with perhaps your internet went down or something like that. That is a direct result of the solar flares. So the photons from the sun cause these changes in the ionosphere. The 1 decibel absorption region. So a specific portion of the bandwidth there, and it's showing you the degraded frequencies there. That's the color scale in megahertz. So here's the most extreme one, right over the Pacific. And we actually did see problems with the SDO website. Keep in mind, folks, that the SDO, the Solar Dynamics Observatory, orbits right around this area. So the SDO performs a figure-8 maneuver here in the central Pacific Ocean, kind of off the coast of South America and Mexico, right around this area right here. So that could be part of the problem for the issues with the SDO website. And we'll close things out with additional spectacular imagery of the closest star. Doing a little spectroscopy here, 2 more different ionized ultraviolet light emission spectral states of ionized iron, 94 and 131 angstroms. Fantastic imagery there of those solar flares. Less so the coronal mass ejection. These are better at watching solar flares. 304 angstroms is the best wavelength for coronal mass ejections. Here's 171 angstroms. This is my personal favorite wavelength. I find it to be the most aesthetically pleasing. All right, and we're going to close things out. By the way, the SDO site is back up at the time we recorded this portion of the video. We'll close things out here in 304 angstroms, sort of looking at the northern hemisphere. This is just the 21st and the 22nd, all available data from the SDO Browse Data site. Again, don't be surprised to see additional coronal mass ejections. This is the kind of event that can cause some power outages on planet Earth. Don't be surprised to see some communications blackouts and so on. Some of the radio bursts associated with these initial coronal mass ejections were very high-speed radio bursts. I would expect some ejecta to show up in as little as 2 days. So 2 to 3 days on that first coronal mass ejection, and I'll say 3 to 4 days, 3 to 3.5 days on the second series. Again, we're going to be keeping an eye on, and when I say eye on, the pun is intentional, any additional coronal mass ejections here, again, as there's still a large sunspot. A second sunspot just rolled in. In fact, let's check the status of that. So here's a colorized magnetogram, and while all eyes are on sunspot 2824, I would also direct your attention to sunspot 2825, which quietly rose over the northeastern limb. 2824 does indeed remain magnetically complex enough to be considered a beta-class sunspot here. It looks like there are some, I don't know, I think all those umbrae may be North Pole. So I think this may be actually an alpha-class sunspot now. Nope, okay. These areas right here, those are South Pole polarity, so that is still a beta-class sunspot. And let's go back to 304 angstroms and close out the video so we can get this uploaded for folks to view. In any case, thanks for tuning in to this daily space weather supplemental. And we'll see you next time early tomorrow, most likely, assuming all goes according to plan for the daily space weather.